And some of it's probably what you've already seen before too. So we talked about matter can either be a pure substance or if it's a mixture. And if it's a mixture, it can either be, there's two H's, homogeneous or heterogeneous. When we talk about solutions, a solution is a homogeneous mixture of two things that are physically tossed together. So the beauty of a solution is one way or the other, you can separate it back out into its components. So we generally think of, there's my beaker. We generally think of, there's lots of S's. So what you have in a majority is called the solvent. And what you're adding is one or more solutes. And the solute plus the solvent is the solution. And I abbreviate solution SOL''N. That's my abbreviation for a solution. So a solution has two or more things that are tossed together, solvents in more amount than the solute. Now, if the solvent is water, if this is water, then we call it an aqueous solution. Makes sense. So a solution is a homogeneous mixture, two or more things that are physically combined. Honestly, as it turns out, stainless steel is a solution. It's just a solution in its solid state. It's a homogeneous mixture of metals that are just physically hanging out, frozen together for all perpetual. The air, a mixture, okay? It's a solution. Air is a solution, okay? But most of our solutions are going to be liquid solutions, in which the thing that's present in greater amount is the solvent, and we add solute to it. So we're going to talk about different ways to express the concentration of a solution. Basically, usually how much solute is there. And like the slide says, usually it's solute, amount of solute, we'll talk about different ways, per a given amount of solution. Okay, usually it's solute per solution. There is another one, and we won't get to it today, and it's solute, a ratio of solute to a given amount of solvent. I don't think we'll get to it today. Solute per given amount of solution, solute per given amount of solvent. So you can already kind of see the whole ratio thing. So we're going to do some problems with ratios. The generic terms of concentrated means you have a lot of solute per a given amount of solution. If it's dilute, you have a dilute solution. That means you don't have much solute per given amount of solution. So those are just generic terms you probably run into before. So here we have the thing that's making it blue is copper 2 nitrate dissolved in water. And it's the same amount of copper 2 nitrate there on the right. It's just dissolved in more water. So you can see the intensity of the blue color is less for the more dilute solute. And there is a technique, and we do one experiment in Chem 2 using a colorimeter. And the colorimeter, not to be confused with the calorimeter, a colorimeter looks at the intensities of colors, and it will actually, you can make a calibration curve, and then you can actually test this to see how concentrated it is. So today we're going to focus on two ways of describing solution concentration, and they both have to do with solute per given amount of solution. The first one is grams of solute per liter of solution. Grams of solute per liter of solution. So that's usually written G/L, where you have to recognize that the thing in the numerator, the G, or the grams, is your solute, and the L, the liter, is your solution. And the other one I want to talk about today is molarity. And so you probably run into molarity before. Molarity is the amount of moles, again, of solute per liter of solution. So I'll put in parentheses, moles of solute per liter of solution. Okay, so it's another ratio. So we're going to do some problems knocking out, expressing solution concentration this way. Now, one of the things, let's see, we talked about the density of water, kind of like this and like this. Now, we actually focus a little bit on when water transitions from a liquid to a solid, it fluffs out. So that's why ice floats, okay? Because solid water is fluffier, less dense than liquid water. But one thing I don't know I necessarily emphasized is if water is still in its liquid state, I'm going to kind of show it with my hands. As it gets colder in its liquid state, it gets smaller, okay? So it contracts. And so liquid water becomes more and more dense with decreasing temperature, okay? I say that because up here, if we are looking at either grams of solute per liter of solution or moles of solute per liter of solution, a liter of solution at 20, you heat it up and it's going to be like 1.04 liters or something like that at different temperatures. Now, this is all to say that when we're talking about grams per liter or moles per liter, we got a temperature issue there. Okay? Temperatures are variable. And so actually when I introduce the other type of concentration, when we're talking about mass or moles of solute per solvent, specifically grams of solvent, then things get better. So that's kind of how that works. So let's do a couple problems. We're going to actually take this same problem, and I draw a lot of, you'll see in my notes, I draw a lot of pictures. Here's my ugly looking beaker. And we're gonna, sucrose solution. One of the good things about drawing or kind of walking yourself through a problem is that you can abbreviate if you want to. So I'm gonna go ahead and say, so 32.3 grams of sucrose, just SUCC, are dissolved in water, and the total solution, so SOLN, solution volume, is 225 milliliters. When I work a problem like this, a lot of times I will put what the target units are. So what is the concentration in grams per liter? So question mark, what we're after are grams, in this case of the solute is sucrose, so grams of sucrose per liter of solution. That's our target. And if you're like, well, Mrs. Snipes, I think you just take that number and divide it by that number, you're right. Okay, so, but we have to fix these milliliters into liters, don't we? So that's basically what we're going to do. So here we go. This is my target, to express it in terms of grams of solute, in this case sucrose, per liter of solution. I take the mass of sucrose, 32.3 grams of sucrose divided by 225 milliliters. Now, how do I get from milliliters in the denominator to liters in the denominator? What do you think?
1,000 milliliters over 1 liter.
Yep, 1,000 milliliters over 1 liter. And I know my slide says solution and solution, but I probably would just put like you said, I probably just put 1,000 milliliters over 1 liter. So now my units will match what my target units are, and that's it. How many sig figs? 3. So I got 144, and usually I would just say 144 G/L, 144 grams per liter. And then if I want to go ahead and I could write sucrose. Or the formula for sucrose, C12H22O11. So it's quite common, maybe even on your test, I know in homework, to kind of take a same solution and express its concentration in different ways. So that's what we're going to do now. And what you're going to see me do is piggyback on this. So you guys have this in your notes. The next thing you can already see on the next slide is I want the same solution, but now I want it in molarity. So the same solution in molarity. So a little bit ago, we said molarity is moles per liter. Moles per liter. Specifically, moles, in this case, of sucrose per liter of solution. So I am actually, you're going to see in my notes, I'm going to piggyback on we come up with 144 grams sucrose per 1 liter of solution. I'm going to piggyback on that. So if I want these grams to be converted to moles, what am I going to do?
Molar mass.
Molar mass, that's it. So as a side, we knock out the molar mass. Molar mass is 12 carbons, so 12 times 12.01 plus 22 hydrogens, 22 times 1.008 plus 11 oxygens, 11 times 16.00. So the molar mass of the molecule, well, that's kind of a fun phrase too, is 342.30 grams per mole. So what's this term going to be? Yep. 1 mole over 342.30 grams. So again, we're piggybacking on what we had before. Now, if you might be saying, well, Mrs. Snipes, we could have kind of like started from scratch and gone back to the raw numbers. You sure could have. You sure could have. Same thing. So, and then if we go ahead and go with what we already know, grams per liter like this, and make our next term the molar mass, the flipped version of the molar mass, 1 mole over 342.30 grams. And again, since I'm only dealing with one species, a lot of times I won't write the C12H22O11. I'll just put 1 mole over 342.30 grams. All right, 3 sig figs. So you're looking at 0.419, and I probably would write it this way. 0.419, big M means molar. And I need to write sucrose, or the formula for sucrose, C12H22O11. It is important, anytime we see a capital M, it is case sensitive, as you may know, and you're going to find out. It's a capital M. We need to know anytime we see a capital M, molarity, we can unpack that. Molarity means moles of solute per liter of solution. So kind of keep that in mind. Cool. All right. So I'm not going to do this one, but we'll just kind of talk through what that would look like. The purple stuff is potassium permanganate, and you kind of have the things you need. Search the letter V. What do we call this piece of plastic? Volumetric flask. A volumetric flask. And they just have one calibration mark on them. And you can actually see in the second one, it's hard to see, but it looks like grape juice. It really does, but I don't think it's very, it wouldn't be good to drink. So you can see that actually we took the powder on that weigh paper, which is a mass of 4.75 grams, added to volumetric flask that has a capacity of 1,000 milliliters. On the side of the bottle, it will tell you to like how many decimals, and it looks like 1,000, probably 0.0, I don't know, 0.00. But anyway, so dump it in there. Here's our distilled water. We add distilled water. How clever, they show the water gone. I'm kind of surprised they got all of that out of that, but I mean, I think there'd be a purple residue. But anyway, they dissolved it up and they got their solution. And in the bottom, it says, please come up with how concentrated that solution is in terms of grams per liter and moles per liter. So it's funny. Well, every once in a while, here's my vol flasks. Oh my gosh, they're terrible. One calibration mark, okay. So you're looking at, I'll go ahead and give it 4 sig figs. That's your solution volume. You added a mass of 4.75 grams. Formula is KMNO4. And then I usually go like this. That means I got it just right. So wow, grams per liter, it's 4.75, isn't it? Okay, so the first one, grams per liter. So I go, 4.75 grams per 1,000 milliliters. You guys would tell me 1,000 milliliters in 1 liter. Okay. Now for the other one, and we'd have to come up with the MM, meaning molar mass of KMNO4, and then we could piggyback on this one if we wanted to, like we did before, 4.75 grams per liter to get to molarity. So then we have to get grams to moles, and you guys told me molar mass. 1 mole of KMNO4 per whatever you got up here was the molar mass. Okay, so that would give you moles per liter molarity. This one is similar. A volumetric flask, a smaller volumetric flask. It tells you that the person went ahead and put 12.1 grams of the solute, which is potassium dichromate, or potassium chromate, excuse me. Potassium chromate, dissolved it up to the line. I think I have a little video to show you, but doesn't this make sense, the A and the B? So you're going to add some water, but you're not going to fill at the top because you want mixing room. You kind of get the whole physical breaking up sort of thing going on. Once it's dissolved, then you go to fill up the line. Now see, I will warn you, if you're ever in a lab preparing a solution, don't forget that one last step. Like if you diluted it up to the line, you have to invert it a few times. Otherwise, if the person who goes to use it is going to have like a diluted solution up here and concentrate it down. I did at my desk kind of make sure that this caption is correct. It says, based upon that 12.1 grams of solute and the molar mass of potassium chromate, you're looking at 0.0623 moles. If we go ahead and take 0.0623 moles, and we divide it by the solution volume, which is 250 milliliters, otherwise known as 0.25 liters, you do get a molarity of about 0.25. I got 0.249, yeah, but 0.250 moles of the solute per liter of solution. So let's take a look at this one. It goes along with this question. So we've got a couple more questions. Okay. This one has to do with a hydrated salt. And we talked about hydrated salts. And I'll kind of show you what I mean with a picture here. But when you take a hydrated salt like this nickel 2 chloride hexa, meaning 6 waters of hydration, hexahydrate, the waters of hydration just kind of leave. They kind of join the solvent because it's an aqueous solution. And then you're left behind the free little formula units of the nickel 2 chloride. So that actually is your solute of interest. So let's see, let's go with beaker. That's probably a volumetric flask. We're gonna dose it with 8.320 grams of the NiCl2.6H2O. Okay, our solvent is water. And then we're going to bring it up to a solution volume of 250.0, so 4 sig figs milliliters of solution. Again, we probably wouldn't make it in a beaker, but that's okay. So I already kind of told you what this looks like. If I kind of take this nickel 2 chloride hexahydrate, I'll show you this way. In water, which we're going to dissolve it in, it basically breaks apart and gives you an NiCl2 AQ, meaning dissolved, and then just 6 H2Os running around. I'll put an L there, running around to be part of the solvent. So we're supposed to come up with the first A. You're supposed to come up with the grams of the solute. It's not the hexahydrate, but it's the nickel, the NiCl2, grams of NiCl2 per liter of solution. And then you're also supposed to come up with the moles of NiCl2, otherwise known as molarity per liter of solution. All right, and there's a couple ways to work this. There in chemistry, and how concentrated solution is one of those calculations that people have different visions of how to work it, and that's fine. I'll catch you on the other side if you do. So the way I'm going to work it, especially for the second part, for the B, the molarity, the moles of the nickel 2 chloride, I'm going to need some molar masses. So here we go. You guys already have these? No. For the nickel 2 chloride, 1 times 58.69 for nickel, and for the chloride, 2 times 35.45. So you're looking at a molar mass of 129.59 grams per mole. The molar mass of just one of those 6 waters of hydration would be this. Molar mass of water, just of water molecules, 2 for hydrogen times 1.008, plus 1 for oxygen times 16.00, or 18.02 grams per mole. You do a lot with water, so it's probably, you guys are going to memorize that one. And for the full thing, do I do this? Yeah, for the full thing, I just I build on what I have above. So for the hydrated salt, you're looking at 129.59 plus 6 times 18.02 to account for the waters. So for the hydrated salt, you're looking at a molar mass of 237.69 grams per mole. I kind of call these kind of doodle calculations done in the beginning. When in doubt, calculate a molar mass. I'm only just sort of kidding. So to work this problem, it's a little different than the other problems because we kind of have to tease out the nickel 2 chloride from the hexahydrate. There's different ways to do that. So let's go for A. We're after grams of just pure nickel 2 chloride per liter of solution. And what we're given is the hexahydrate, 8.320 grams of the hydrated salt. And yes, I probably would take the time to write out the NiCl2.6H2O. I'm going to go ahead and put that over the 250. I guess I could have. Now I see I'm not. I'm going to hold that thought. I'm going to try to go ahead and tease out the mass of the anhydrous salt, so as to speak. I know that that last molar mass, we said that the NiCl2.6H2O has a molar mass of 237.69 grams per mole. So I can put 1 mole of NiCl2.6H2O over 237.69 grams of NiCl2.H2O. So I'm going for moles of NiCl2. How many moles of NiCl2 are there per hydrated unit? How many moles of NiCl2 are there for 1 mole of NiCl2.6H2O? 1. Just 1, exactly. And that's my third term. Kind of wraps around. Exactly. So if we just go for 1 mole of NiCl2 over 1 mole of NiCl2.6H2O. Now what's canceled, the grams of course canceled up here. Now the moles of hydrated salt cancel, and we're left with moles of NiCl2. And I'm kind of working this in steps. You could do it all in one fell swoop too. What, 4 sig figs? So the moles of the anhydrous salt that I have in that mass are 0.03500 moles of the pure NiCl2. So working it stepwise. Now, to get to, now to get to molarity, all I need to do is take those moles and divide it by that volume. That's what I've done here. Except we have to do what we did before and introduce a term to make liters in the denominator. So if you put 0.03500 moles of NiCl2 over 250.0 milliliters, and I go ahead, my next term will be 1,000 milliliters over 1 liter. Phew, That will give me units of moles per liter, which is awesome. 4 sig figs, right? So this is a good example of I had to be careful, and in the problem, it will tell you how precisely you know the volume of the solution. So make sure you don't blow that up. So we're allowed 4 sig figs, and I probably would write it just like this: 0.1400 m as in molar, and then list your solute, NiCl2. So I did B first, and actually that's a good point. If you have a single solution and you're supposed to knock out how to express the concentration of the solute in different ways, you don't have to go in order. So now I need to backtrack. Now that I know the moles per liter, I can get to grams per liter using the molar mass of that thing, right? Here we go. I'm going to piggyback. We said it's 0.1400 molar. That means 0.1400 moles of NiCl2 per 1 liter of solution. And if I want grams per liter, I have to introduce, a few slides ago, you had the molar mass of NiCl2 as 129.59 grams per mole. So if I put 129.59 grams of NiCl2 over 1 mole of the NiCl2, the moles of NiCl2 have canceled. I'm left with units of grams per liter, which is exactly where I wanted to go. And again, we've been careful rounding like we needed to all the way, so I'm allowed 4 sig figs. So I probably would just write it 18.14 G/L of the solute NiCl2. These pesky waters of hydration. Gotta love them. All right. Well then, here's an alternate way to do it. Going for the grams per liter first. So this is what I kind of started to say before. If we just go ahead and recognize, go ahead and take this 8.320 grams NiCl2.6H2O divided by 250.0 milliliters of solution. And then somehow we have to get from that mass of the hydrated salt to just that mass of the salt, the anhydrous salt. So if you go back to a few slides where we had molar masses, honestly, the way this works is for every 1 mole of the hydrated salt, for every 237.69 grams of the hydrated salt, 129.59 grams of that would be the NiCl2, the anhydrous salt. And that actually came from the molar masses from MMs. In that case, our grams of the hydrated salt, grams of nickel 2 chloride hexahydrate, cancel, and we actually were almost there. Unit-wise, we have grams of NiCl2 per milliliter solution. We have to, of course, introduce one more term, 1,000 milliliters over 1 liter. And now my milliliters will cancel, and we have units of liter in the denominator. And that's perfect. You're looking at 4 sig figs, it's what you're allowed. So you end up, not so surprising, with 18.14 G/L grams of solute per liter of solution of the NiCl2. And I think probably my next slide just says, remember with the sucrose, we went back from, we can piggyback from this grams per liter to moles per liter using the molar mass of the NiCl2. All right. Finish up with one more problem. I use the same beaker. All right. So in this one, we're given two pieces of information about the solution, and we're supposed to knock out the molarity. Now, I'd say very rarely, well, temperatures are one thing. Sometimes I'll give you a temperature and you don't use the temperature in your calculation, just because, like we talked about, water expands when it's warm and contracts when it's cold, so temperature. But usually every number I give you, you're going to have to use. And they're like puzzle pieces. They're like, oh, how will I use that to benefit me? So let's see. They were dealing with an acetic acid solution, and I abbreviate AA is equal to acetic acid. Again, if you make your own picture, you can make up your own abbreviations, just kind of say what it is, what the deal is. So if we have 76.0% AA, acetic acid, that means 76.0 grams of AA, acetic acid, per 100 grams of solution. That's what that means. So that's weight percent, mass percent. And then it gives me my density. And so the density is 1.07 grams per mil. I should never see you work a problem. You're going to have to use this number, but you should never leave it in G/ml. You're always going to unpack it. That means 1.07 grams per 1 milliliter, but I need to be more specific than that. When I do a density, it's the whole, I'll put a subscript SOLN. It's the density of the solution. So this is 1.07 grams of solution per 1 milliliter of solution. Now you might be like, well, Mrs. Snipes, how do I know when I have to be explicit like that, or does it not matter? I guess in looking at this, this should be a clue why I need to be really specific about it, because I have grams of acetic acid and grams of solution, so I have to say what grams this is. I think my next slide just kind of unpacks those two. Oh, so question mark, what are we after? What's our goal? We're looking for moles of AA, moles of acetic acid, per liter of solution. That's what we're after. That's molarity. All right. So this is unpacking those two that, like I just did on the board. You need, whoops, sorry. You need to unpack. What does 76.0% mean? It means what I said. And then what does 1.07 grams per mil mean? All right, so those are our puzzle pieces. So can you already kind of see, if I'm after moles per liter, specifically moles of acetic acid per liter, I can use, this is one of my terms, I'll use the unflipped version of this, okay? And actually, if I put these two together, if I multiply these two together, I'm thinking grams of solution cancel, aren't you? And I'm left with grams of acetic acid, which is CH3COOH per milliliter solution. Heck, I could slap on a term 1,000 milliliters or 1 liter, and I'd be at grams per liter. And we know how to get from grams per liter to moles per liter, so use the molar mass. So here's the molar mass, CH3COOH. For carbon, we have 2, so 2 times 12.01. Plus hydrogens, when you collect them, we've got 4 plus 4 times 1.008. Oxygens, and we'll talk about why do we break these oxygens up in the formula. But for oxygens, we have 2, so 2 times 16.00. And so the molar mass you're looking at is 60.05 grams per mole. So we're going to use these as puzzle pieces. Use these as puzzle pieces along with the molar mass to knock this out. So where do you start? Well, wherever you want to start. Like I said, this is where sometimes when I'm grading it, sometimes students go one way, sometimes they go another way. But we know that we're going to want amount of solute, and molarity is moles of solute, but if I put grams of solute on the top, I'm probably going to be in good shape. 100 grams of solution in the bottom. Of course, there's no uncertainty brought by that 100, remember, because that's unpacked by definition, so we have 3 sig figs there. If I go ahead and introduce the molar mass as my second term, it wouldn't have to be. But this is where if you've abbreviated, you can do AA instead of the CH3COOH. But the molar mass for acetic acid is 1 mole of AA, or CH3COOH, divided by a mass, or per mass of 60.05 grams of CH3COOH. My grams of CH3COOH have canceled. I'm left with moles of CH3COOH per 100 grams of solution. Now, if I introduce density, the non-flipped version of density, which is 1.07 grams of solution per milliliter of solution. And if these were all 3 in line, it'd be easier to show you, but can you see where I do this one? So now my grams of solution cancel. I'm left with, in the denominator, milliliters of solution. Of course, my grams of acetic acid have canceled here. We have moles. So I have moles per milliliter. So one more term like we've been doing, 1,000 milliliters over 1 liter. And now my milliliters will cancel. And we'll be left with units of liters, which is molarity. Looking at 3 significant figures, again, don't, if you're given a weight percent 76.0%, please do me a favor and know that they took the time to give you that trailing 0 after the decimal for a reason. All right, 3 sig figs. Okay, so you're looking at 13.5 molar. 13.5 molar CH3COOH. And what that really means is 13.5 moles of CH3COOH per 1 liter of solution. So again, there's, oh, you know what? I don't think we revisit solution concentration in general chemistry 2. So I think for general chemistry 1, this will get us down the road to all we need to do. Okay? So many things you need to take general chemistry 2 in order to have things make more sense. We talk about acid bases in general chemistry 2. That's, you know, a big thing, because in order to talk about acid and bases, you're like, we need. But, you know, I know it's protons and hydroxide ions, but you need to talk about chemical equilibria, and you can't talk about that until that's a whole chunk in chemistry. But what I did the other day, recently, was to like go in Canvas, and you know how I have in your grade book, it should have a line that says extra credit or something like that. And if you if you changed your picture, which I enjoy looking at your pictures, if you change your picture to something, profile pic, love you, and you can, you get 10 extra credit points. And then the other day when you guys did that stoichiometric calculation, you got 10 extra credit points. So, and on there, what I did was add how else you can get 10 extra credit points. And honestly, I'm serious. If you download a periodic table app to your phone, you tell me, or like I did that, that cheesy equation balancer, download it, that's 10 extra credit points too. So anyway, if you think of anything else cheesy, you can get 10 extra credit points. All right. Remember, those are only good for missed assignment points, not for labs, not for tests. See you on Wednesday. No lab tomorrow.